Hello everyone, today we're going to talk about the D-FINE-seg repo, previously known as custom define, and as you probably understand from the naming, now it includes a segmentation model. That was actually the biggest update to the repo, but there were some other things that I will go through. So first of all, the segmentation head. It means that this repo now supports instant segmentation and object detection tasks. And what we did, we took the original architecture from the D-FINE paper and we added a segmentation head. Everything else stays as previously. You can train both tasks. The overall pipeline is very similar. And I will talk about some differences that you should know about. But if you want to dig into the architecture itself, we have published a paper. You can find all the details about the architecture, about why we picked what we picked. But basically, the idea was to stay relevant in the real-time instant segmentation space. We were, as a baseline, we used a YOLO 26 segmentation model. So we were trying to be as close as possible with latency, so the mask head is actually pretty lightweight. As you probably can see, the README was fully rewritten to be easier to follow, but right now what I want to talk about is the one and probably main change or difference to the segmentation model and the object detection one. Is basically the data preparation part, the thing that you need to do yourself before you start using this repo. And as previously, we need only two folders, images and labels. Inside the images, you have all the images that you have. You don't need to do the splits beforehand. And same for labels. Labels are in .txt format. This is a YOLO format. It's the same. For a detection, you have class ID and then bounding box, and for the segmentation task you have again class ID and then pairs of XY, XY in a normalized format. Okay, so when you have these two folders, you want to run the make split command, this one. It will create you a CSV files. So these two folders you should collect yourself. As you can see, there are TXT files there in a format I just described, normalized. Same for images. And finally, these two files will be generated by the make split command. This is just a small table with the name of the image. Okay, the next part is, as previously, use config.yaml file to update all the variables that you need. The main thing is that there is now this task detect or segment field. Also important ones, the path to the folder that you want to use for this project. As an example, I can use this one. This is how I do it. I have a folder for example, for a taco dataset, and I have my data here. And this output folder will be generated by the pipeline. You see a bunch of things here, debug images. You will see how data is getting into the model after pre-processing. A couple of examples with the labels with bounding box and the annotation of the mask too. Evaluation predictions. This is what model outputs in a blue for the bounding box and green for the ground truth. And for the mask, ground truth again has a green color, but prediction will have different colors. In this case, it's bluish. Bench images, same thing, but when you run make bench to benchmark all the formats that you will export your model to, and models is the main output folder where you will find the models itself, the exported models like TensorRT. You will find some plots, confusion matrix. So yeah, all the good stuff. Okay, when you're done with the updates of the config.yaml file, you can basically get to the training. That's all you needed to do. Now you just run make train. It will start the training process. You will get your model. I will just show how it looks like. Just run make train. We will talk about this one in a second too. But basically, it starts training. In this case, the task is segment, for instance, segmentation. And yeah, for the next commands, they are pretty much the same as before. You can run make export to ONNX, TensorRT, OpenVINO, and now CoreML. Make bench to check all of these formats and see how they work. CoreML will only run on Apple Silicon, so it's not integrated into make bench, but you can do it for your Apple Silicon machines. And yeah, everything else is probably less important, but I like to use these commands. For example, check errors. I run this to find out the cases where model was struggling, basically the model's mistakes on the training set and validation set, because it means that either model can't learn it for some reason, or maybe there's an error of the ground truth. So that's important to know. Test batching, it helps me to understand what should be the optimal batch size for a specific model and specific GPU. And this one, again, I will talk in a second. But for now, let's see how our process goes. Our first epoch is done. We get very, very low scores because it's for first epoch. And for example, if we open up a similar model segmentation S, we can see the logs from the training, and we can see that the first epoch, everything is around 0, and from epoch 5 it starts to get better. Okay, I will stop this because we don't need it and get back to the README. Now let's talk about some other updates which are pretty nice. For example, DDP support, which is a multi-GPU training. You use this to make your training process faster. Obviously, with several GPUs, you just load one model per GPU. And basically, you will get speed up in your training process if you have several GPUs. Another thing is the export for the OpenVINO. It now supports int8 quantization. It's accuracy-aware quantization, so it tries to quantize the weights, and then it runs the accuracy test on your validation set. And if the model is good enough, it will stop. If it's not, it will try to optimize more. It actually can take a while, so this is a separate command, as you can see here, just because it really might take a long time. It might run in like 10 minutes or several hours. To configure that, you can use, in the expert part, there is an OpenVINO int8 max drop. So this value says what should be the maximum difference that you allow from the baseline FP16 model and quantized int8 model. So if you see that, for example, you had an instant quantization to int8, you can actually go and say, okay, I want 0.01. But if you see that it takes a very long time and you don't have that time, you can go a little bit higher, as I did in this case. This is, by the way, in absolute values. It's not relative, it's absolute drop in the F1 score. Yeah, and one more update. Again, CoreML export to run on Apple Silicon. I tested it on this M1 Pro MacBook Pro, and results were pretty good. Actually, I will now get into the benchmarks, but I will start with a more like high-level benchmark. As I mentioned previously, we were trying to get the same latency as YOLO 26. All the tests we ran, we did on TACO dataset. It's pretty hard, but small dataset. I will show some examples. There are 59 classes, 59 labels of different trash or waste in different environments. It is pretty challenging because like there are a lot of different classes. and only 1500 images. And we used both detection, object detection, and instant segmentation tasks here. We tried both, training on bounding boxes or masks. And here you can see a quick graph where we compare D-FINE-seg with Yellow 26. Here, when you see D-FINE, it means that it's an object detection model, but trained with this repo. And D-FINE-seg means that, again, this repo, but the segmentation model. You can see that around model size M, Yellow 26 is actually very close to D-FINE-seg, but in other places you can see that we get better scores. We reported results on this TACO dataset. We spent a lot of time working with it, but also we did check a bunch of other datasets. We actually saw that results are very similar. Although we didn't train all the sizes of models, we just worked with one or two particular ones in other comparisons. So yeah, here we show TACO dataset, which should be representative. Same thing we did with DroneViz dataset for only object detection, because there are labels only for object detection. Again, we got pretty good scores. I can show it here. And yeah, we have a bunch of benchmarks here. If you want, you can see classical mean average precision scores for both tasks. Actually here, again, M model for YOLO was better, but everything else, D-FINE-seg was better in all other sizes. And also we have format comparisons. For example, just running on the GPU, the results that you get with Torch, full precision with TensorRT, and half precision with TensorRT, you can see that latency drops dramatically, 4 times, and there is no accuracy drop, which is very cool. You don't lose anything. And if you run on the GPU, on NVIDIA GPU, please export to TensorRT. Yeah, same for the detection task. The results are great here without any meaningful accuracy drops. We also have benchmarks for the Edge device, which is a small Intel-based mini PC with N150 CPU. It has IGP cores, so we ran on them. And specifically for Apple Silicon, again, I tried only on this particular laptop, and I got good scores. I got 2 times speed increase in comparison to the Torch MPS. So in both cases, it ran on the GPU. So this is pretty good. The only thing is that float point 16 didn't really work for me. Latency was a little bit higher. I don't really know why, and for now, CoreML defaults to FP32 when OpenVINO and TensorRT defaults to FP16 in this repo. And that's pretty much it. That's the main updates that we had. And from now on, after the paper release, we will also be writing the main updates to the changelog. You'll be able to find it here. For example, here we updated the nano version of the segmentation model to improve the mask quality, and yeah, implemented CoreML expert. So yeah, you'll be able to find more updates here in future. That's it. If you will have any questions, you can contact me via email or my LinkedIn. I will try to help when I can. And that's it. Thanks, everyone.